Mr. Louis Moreau. He is from all over the world, but recently moved up to Quebec, Canada. His title is Play Safe with Safe Interlayers. There's only a very short introduction here, so I'm going to embellish a little bit, and he's going to be, it'll be good. With more than 30 years experience, I think we're supposed to say more than 5 now.
More than 5?
More than 5 years experience in the glass industry. He carries an eclectic mix of international management and technical knowledge in melting glass, sputtering high-performance coatings, glazing large buildings, laminating amazing glass structures, and mastering superior glass fabrication. That's all it says here. But what you need to know is that Mr. Moreau has single-handedly worked in pushing ASTM to produce a standard on a word I could never say until he beat it into me, anisotropy.
Pretty good.
And he's also helped to move along the air traffic control standard for cab glass, for vision glass, and whatnot. So Louis has been a tremendous asset to us and a great help. So we thank him for coming to North America. And he keeps moving further away and north and more north. Soon he's going to be living in Santa's Village on the North Pole. But we will let Louis give Play Safe with Interlayers. Thank you very much.
Thank you, Julia. That's a good introduction. It's very pleasant to be with you this morning. This is really a fun for me to be in Tampere. Last time I was here was 2019. I'll talk to you about it at the very end of the presentation if I have time. Right now, I don't know if there are laminators. There's probably laminators behind you in the crowd here. Sentry glass has become very scarce. There's not much sentry glass on the market, and people are looking for other solutions. So I just want to share what I've been working on, what I've been doing with stiff interlayers, so you can avoid some mistake and avoid problems in the future. Let's start. So. I'm going to first, I always like to take a historic look at a problem. So I'm going to start with the invention of structural glass. Structural glass, so glass that people can walk on, is quite recent, or structure of glass that support glass, that's quite recent. It started, I would say that's the start date for that, 2002. And if you look at the laser, if you look at the list, there's 2 persons on that list that are here today, James O'Callaghan and Graham Colt. So both these guys have set up the beginning of structural glass, or glass supporting people. And that was the original Apple staircase in New York. And if you dig a little bit into the patent request, you're going to see that there was 3 things that they talked about that was important. The use of Sentry Glass Plus, the use of titanium in breads, and then the use of anneal glass. So this is the 3 component, the base component that they set up. And that's really what set up the whole thing. So you use an ionomer interlayer because it's very stiff, because it doesn't move in time. You use titanium insert because they don't expand, so the coefficient of expansion of titanium is identical to the glass. And you use anneal glass so you can avoid a series of problems. So let's look at all those 3 subjects. The stiff interlayers. So here I took something from a Curry brochure just to show the shear deformation. What is shear deformation? So when you have 2 planes of glass and you put an interlayer, when you stress the glass, you get a deformation in that. And the shear, or the shear modulus, is what prevents you to shear it, in fact. So I took a series of of different material. Rubber, that's the rubber you use in tires. PVB, 4.2. And again, look at the title, it's at 25 degrees for 3 seconds. A stiff PVB and ionomer at that temperature and time react about the same way. Nylon will be the hardest plastic in the list. Then you go into metallic compound and finally diamond at the bottom. So what I like is to, because there's a relationship of time and temperature, I like to show that on the same graphic. So this is Saflex R, a regular PVB that is being used everywhere, ubiquitous. So you see that there's a little resistance right at the beginning when you have low temperature and low time. But if we move to stiff PVB, so you can see that this resistance becomes very, very large at lower temperature and lower time. The ultimate centric glass comes with a much broader range in both directions. So you can use it at a higher temperature, you can use it at a longer time period. So at the end, what I would say when you design for structural element, this value becomes very important to still have a residual shear modulus over 10 years or 30 years or 50 years. So this is what centric glass brings to the equation. So just a summarize, PVB, it's a safety product. It was invented, the purpose of PVB is to retain the glass fragment together. And it does it very well. Then the stiff PVB works in short loads at normal temperatures. So you can use them very good. In fact, it's a bit stiffer than ionomer at 20 degrees C. And it's very good for wind gust, for a facade. You can use that and get your rigidity that you need for short period, for short burst. And you can also, depending on codes, work it for balustrades. And it works pretty good at 0 degrees C, so it's good in cold temperature. So you still have 97 megapascal of modulus for 1 month at 10 degrees. So it's very good for snow loads. So when you have snow on top of your laminate, it's cold by definition, and it will, as long as the snow will be there, the stiff PVB will be cold and stiff. But you have to be careful because it softens rapidly when you have rising temperature. So it's not super for Dubai. But if you go at very high temperature, if you have a fire or something like that, the stiff PVB is quite good because it remains like a gel. It doesn't flow. It is really something that will prevent the paint to slip at high temperature. And finally, so for long load, it's still good for safety, but you don't have the stiffness, but it's still a safety product for long loads. Ionomer has a very wide range of temperature and time, so you can see that. And it's actually it's the only solution for permanent load. And right now it's still a monopoly. So there's only one supplier of ionomer. There might be a second one somewhere in China, but we don't know about it. But again, you have to watch for its property at very cold and very warm temperature. At very warm temperature, it will allow glass to slip. And at very cold, it becomes very brittle, and it doesn't function as at room temperature at all. So previously, Stefan showed a video of centric glass. So this is a 9-ball drop with the 4.5 kilo for a P5A. So P5A is supposed to support nine hit, and that's the first hit of a centric glass with that. So you see the ball went through right at the first hit at minus 19. This is 0 degrees Fahrenheit. Another thing we talk about, the embedded metals. So again, fundamentals, the expansion coefficient of glass is 9, so 10 minus 6 meters, so micrometer, per meter per degree C. Titanium is about the same. Stainless steel is about twice, and aluminum is even worse. So here's a project I did with somebody on the audience, where I use a 900 millimeter bar of titanium. That was a door that was stabilized and hold by a titanium rail, and this is the patch fitting for the hinge. You see it installed in position. That has, even if you have 900 millimeter of material, nothing has happened because you have the same coefficient of expansion. And by the way, that was the handle of that door. I've also been using embeds for balustrades, for rails, in different stringers for staircases. And I've been using the same embeds to hang this sign, like the H&M sign here is hang with the metallic embed stuck into the IGUs. But recently, when I was working at Agnora, we had a customer that asked us to laminate his own pucks into the laminate. And it has resulted in something, oops. So you see the, and after a few months of installation, this appeared around the fixing point. So I was a bit concerned with that. So I started experimenting with this assembly in our shop. So I created laminates with different inserts and see how they react when we change the temperature. So this one is the one that I have most documented. This is an aluminum embed that is commercially available in the market. And so you see the back face and the front face into the laminate. So that was the first step. It's in a 12 by 12 laminated on 10 on 10 anneal glass. So what I did is I freezed it. That's Joe. That's Mr. Fresh freeze bar. But I still control the thing with my thermocouple. So froze it just informally at minus 19 for overnight. And that's the picture of the back the next morning. So you see that the glass, the anneal glass, has cracked because of the difference in coefficient expansion. It's pretty dramatic. And again, you see this delamination in the glass. So I was a bit curious to find out what was this. So you see the back view and the front view. You see it's very, very uniform around the puck. The delamination is very uniform. So I was wondering what's there. So what I did is I water jetted the puck and to find out what was that. Was it the glass that was delaminated, or was it an adhesion failure? So I was able to, so you got the front view and the back view. So I was able to easily pull the thing. Once I circle it, I was able to pull the material beside them. So you can see that the Sentry glass surface is perfectly, so it's a pure adhesion problem. And the glass itself, and it's on both sides of the Sentry glass at the end. And you can see also that there's two failure modes. There's also a glass cohesion failure mode in here. So here I still have a Sentry glass with glass around it. So if I look at the glass itself, the surface of the glass was sheared by the force. So that is quite important. that's what happened in this case. So this is the puck that the customer has done. So at minus 19, when I freeze it, I really get 100% failure. So either the interlayer is the adhesion is not there, or the glass is cracked around the embed. So what I did is I wanted to test what I've installed at H&M and everything. So this is the original one, and it's got a Delrin washer between the stainless and the glass. And that's before and after. So you see that after the Delrin color has changed a little bit. So you have delamination in the Delrin, but there's no problem around the Delrin ring. So the Delrin act as a bound breaker and prevent the glass from breaking and keeps the attach point intact. So my recommendation is use titanium and sleep well. You're going to cost a little more, but it's worth it. And if you use aluminum or stainless steel directly, you will have failure, either a delamination around it or even the glass breaking. And if you want to still use small insert of stainless steel, you can do, but use Delrin as a bound breaker so you don't break the glass and you don't have things. But doing that reminded me another problem that I had back in 2014. This guy. This is a complete delamination. This is a triple 12 laminate. So it's 3-ply of 12 millimeter with the famous aluminum embeds in them. And during the install, when they reached the roof, the middle layer of that triple laminate broke. And it resulted in having the whole unit taken apart. And the reason that happened is basically when you break tempered glass, it grows, it's larger, and centered glass is so stiff and it sticks so well to the glass, it's sheared the surface of the glass. So your starting point is you have your layer available, but when you break it, it becomes a bit larger, and you actually shear the surface of the glass. So if you plan to have more redundancy with a third layer, in fact, what you're doing is not, if you use tempered glass in the middle, you may lead to a catastrophic failure like you saw before. And I use this analogy. This is glue chip glass. So it's a glass that was used as decorative during the 1900s. And in fact, you can shear the surface of the glass with horse glue. And that's what people were doing then. It's the same thing that happened with the century glass. So when possible, use anneal glass so you won't have that. If not, use heat strengthened so you will have less expansion. But don't use fully tempered inside the laminate. And that brought back, this is James at Technora, and that brought back, when we did the replacement, back in 2014, on that project earlier, we ended up that. But even when we delivered the replacement glass, it broke again. But this time, it's the third layer. It was an outside layer, so it didn't delaminate. But it's only last fall that I realized that what started the whole breakage of the outer ply was the aluminum plug. So because it's tempered, it just pulled the glass and triggered the whole light to become like that. So, and it was not a very, very cold. It was not at minus 19. It was just the transportation from Collingwood to New York. So that's my saying about multi-layer laminate. The bonus section, optical. The other thing you need to know about stiff interlayer, centric glass or ionomer, is that it is hazy. It is a hazy material. So at one point, so this is in Montreal, it's a 14-layer laminate. So at one point, you have to decide or the architect has to decide what he wants, but you could have used steel or another material then instead of glass, because you kind of lose the purpose of glass being transparent. It becomes a milky thing. So you have to be aware of that when you use multiply laminate, because this will happen with an ionomer. Basically, it is hazy, and you have to take that into consideration. So PVB, the other thing is the yellowness index. Stefan was talking about it also. PVB, all the major providers now have extra clear PVB that are less yellow. Stiff PVB, the original product has high yellowness, and when you use it in balustrade, it makes a bright yellow edge. So new products are proposed by the various to resolve that issue. And ionomer will have a very low yellowness index, so that's one of its property. Now, the PVB has very low haze. The stiff PVB has a low haze, but you have to be careful when you use the ionomer, because the haze develops when you cool the material in the autoclave. So you have to cool it very rapidly. But when it comes to very thick assembly, it becomes impossible. The physics of cooling makes it impossible for you to not have haze. And that's what, so you need a rapid cooling autoclave to do that. And fast cooling, it's difficult to achieve in hot box, I mean, with center glass. So if you have a processor that doesn't have an autoclave, you will have a high level of haze when you use ionomer. And the more you stack, the more you have haze. So the bonus, I said that I would talk about it a little bit. It's just this. So my last presentation in 2019, we said that we were working on a new standard for anisotropy, so measurement of anisotropy. So that has come up. So we now have the C1901 that was published 1st of January 2021. It's a standard that shows you how to measure and how to obtain a good value when you want to measure anisotropy in architectural glass with the modern scanners. It also describes which scanner works and which scanner don't work. So it's a valuable one. It doesn't set any limit because anisotropy is very, very complex, and we didn't want to go there at the beginning. So use it as a reference if you want to specify a level of anisotropy with a piece that you know you can measure it, specify, refer to this, and everybody will have the same results. Last year, the English version of this specification, it's not a standard, it's a specification, a DIN spec, is also pretty much like mine. I mean, it's based on the same, use the same terminology and everything, so that's the DIN one. The DIN one has set some values, but you have to be careful because it is only for monolithic clear glass. So and the range that was given in the DIN spec is what was something that was proposed. We looked at it. The same committee that did the 1901 decided not to introduce that at this point because anisotropy is pretty complex. And when you talk about colored glass, coated glass, glass assembled in IGU and everything, you have to be careful when you set limits because there's a lot of phenomenon that happens there. So I thank you very much. So this is my presentation. If you have any question, I'm available for that. I also thank Agnoros for providing all the samples and Verdage for having water jet my laminates.